right, it's 2:02. Let's get started. So hello everyone, welcome to Ask Seminar Series. I'm John, the seminar coordinator, and together with me is Miss Kathy Mendel, and she's our communication specialist. And Kathy and I will be today's moderator. Our associate director, Ralph Ferrero, also joined us, and he will be introducing the speaker. Just so you know that the seminar is being recorded. And we will put the recording on our YouTube channel. So please feel free to check it out. And you are welcome to bring up any questions after the speaker's presentation. And today we are excited to have our speaker, Bill Blackwell, joining us. And before he gets started, I'm going to let our Associate Director, Ralph Ferrero, to introduce Bill. I saw our director, Alan, is here as well. So, Ralph, please go ahead.
Yeah, thanks, John. And yeah, it's a pleasure to have Bill Blackwell give our talk today. Bill and I have known each other for a while, both done some microwave work in the past, and he continues to do it. So yeah, Bill's with MIT Lincoln Labs. He leads a number of projects involving atmospheric remote sensing and development of new sensors. Bill serves as editors of a lot of journals and also on a few NASA science teams, and he's also involved with the National Academy studies of radio frequencies, which is really important at the microwave. And he's won numerous awards in his career, and including the NOAA David Johnson Award. Really just done a lot of breakthrough work in microwave remote sensing, and he's going to give us an update on the TROPICS mission, which is a really exciting mission and could pave the way for really what our future remote sensing constellation will look like down the road. So turn it over to Bill.
Great, Ralph, thanks a lot. It's a pleasure to be here. Let me bring up my slides. And as I'm doing this, let me just say that I've been watching the attendance list. So a lot of familiar names there. Hi to everyone. I look forward to seeing you all again in person at some time. We're getting closer. But for now, we'll continue with these virtual seminars. Can you guys confirm that you can see the slide there?
That looks good.
And let me, okay, well, you know what? I've actually shared the wrong presentation. So let me do that again. Let's try this one. Okay, there we go. Sorry. Share this guy. Right, so I know how to fix this. All right, here we go. So as Ralph pointed out, this is a very exciting time for the TROPICS mission. And now can you see that one?
Yep, that looks right.
Yes. Yeah, so a lot of things going on. The most important of which I think is that we are very close to launching the Constellation mission. So I'll get to that in the talk. But Astra is going to launch the 6 satellites, we hope starting next month. So it's right around the corner. And so part of the talk will be, I'll explain the Constellation mission and talk about why I think that is going to bring some really nice things for future systems. But the Pathfinder satellite we launched, that's the 7th one that we built. We launched that last June, and that has provided some really great data. So I'll talk about that data and what that means for the constellation. So a little bit of an overview and a look at the Pathfinder data and a look forward. So let me get going here. All right, so it's pretty easy to motivate the need for a system like TROPICS. We're trying to make measurements of tropical cyclones specifically, but dynamic events where we really need to capture what's going on in the observations with revisit times, on the order of, tens of minutes or half an hour. So, we can observe the systems as they are evolving, on their native timescales. So here's one example. A few years ago, a Hurricane Dorian with many deaths and billions of dollars in destruction. So there's a lot at stake in terms of forecasting these systems and doing the disaster management and so forth. So to do that effectively, we need good forecasts. And for good forecasts, we need better observations, essentially. Better observations and more frequent observations. So that's what TROPICS is intended to provide. So this is a NASA research mission. So we're trying to fundamentally understand the processes for storm formation, intensification, and then use that to improve our forecasting of track and intensity is really the end game for all this. So there's a lot at stake here, and the storms, of course, are ubiquitous and looking like they're becoming more frequent. So here's a little bit of history in terms of the number of the storms that we have, and an example a few years ago of how many we might have at the same time across the globe. So it's a challenging observing problem, right? So we've got to observe the entire globe with sufficient spatial resolution to capture all the spatial dynamics, and with the temporal update to capture the temporal dynamics. So that produces a pretty profound challenge in terms of how you actually get sensors into space to do all of that effectively at price points that we can afford. So TROPICS is intended to address all of that. So the fundamental measurements that we need to make for the tropical cyclones are shown here. So one of them is the humidity and the environment of the storm, which in many ways is the engine that fuels tropical cyclones. So we need to make measurements of the humidity profile, which we can do effectively with a microwave radiometer or infrared spectrometer, for that matter. I'll talk about the relative merits of these later. So we need three-dimensional profiles of things like moisture and temperature. So for example, we want to be able to resolve the hurricane eye and look for the temperature anomaly. That's the red region there aloft at about 8 kilometers, which tells us something about intensification. So we can do that with a temperature profiler. And of course, we want to measure precipitation, which passive radiometers in the millimeter wave are okay at doing. I mean, they can produce structure and respond to ice scattering. So it's a useful but not great measurement, but it's good enough to say something about things like the symmetry of the rain bands and our replacement of cycles and things like that. So taken together, we need to make 4-dimensional, 3-dimensional plus a time variable observations of all these important variables in the microwave. So there are a number of ways that you could think of that we could do all that. Radars, which we can base on the ground. Radars in space are very hard to do, but they are coming. We have a couple of them that have been demonstrated on big satellites and even small satellites. So I think you'll start to see radars on smaller satellites being fielded now. But we don't have that yet, and certainly on a global scale. So there is some sparsity in the coverage and the temporal update of the radars, but they have great data when you have them. We can drop instruments out of aircraft, but again, you have the data sparsity issue there spatially. The infrared systems I mentioned earlier are fairly good at this. The problem with the infrared is that they can be blocked by clouds. So the interesting thermodynamic structure below the cloud top is sometimes covered up by the cloud top and obscures what the IR can see. So passive microwave sounding is a nice compromise. It has useful resolution, and it can penetrate the clouds to get at the temperature, the humidity, and the precipitation to say something about what the storm is doing and what it might do next. So TROPICS is a constellation of cross-track scanning microwave radiometers operating from 90 to 205 gigahertz. So as you might imagine, the microwave measurements are very useful for predicting tropical cyclones. Here is a recent report out of ECMWF where they have looked at the relative merits of a number of types of data. And for the 36-hour forecast, at least, the microwave is by and large the most important for both track and intensity forecasting. And this is largely due to the good global coverage we have and the ability to penetrate the cloud tops with these frequencies. So the profiling, I think many of you know the story here. We use channels that are sited near absorption features, either oxygen lines in the microwave or water vapor lines. So we have channels near the 118.75 gigahertz line that we use to derive a vertical distribution of atmospheric temperature. So we have 7 channels in TROPICS that are sited off the 118 line. And by progressively moving away from the line, you can penetrate deeper into the atmosphere to build that 2-dimensional profile. And as we scan across the satellite track, we get that third dimension of cross track. So we've been making these measurements, of course, for many years, right? So NOAA has an operational polar and geo network. The polar network's got microwave and infrared sounding, but these spacecraft are big and expensive, and justifiably so. They do a lot of really nice things, and they do them very well. The regret is that we don't have very many of these, right? So you need to wait, on the order of 3 to 4 to 6 hours for the next satellite in the polar constellation to fly over a storm before you get the next shot of it. So we have, over the last decade or so, been looking at ways that we might try to mitigate that problem. And one thing that we've come across is a proliferation of smaller targeted spacecraft, where we can leverage a lot of the CubeSat ecosystem, if you will, the new space, that providing all kinds of almost commodity capabilities for things like spacecraft buses and ground stations and mission operations and launch. So we figured out, how to build these very small, relatively affordable satellites. And the idea with TROPICS is to scale that up and proliferate a constellation so you can have a very high revisit rate, down to, for TROPICS, about 45 minutes instead of the 6 hours. So that effort has required a lot of technology development that I just wanted to highlight in this slide to take you through where we've come in the last 10 years or so. And the NASA Earth Science Technology Office has been really critical in providing some of the funding to take us from the left to the right across the page here. So the first thing we needed to do, as you can probably imagine, is figure out how to miniaturize a system like the ATMS or the AMS2 that you're probably familiar with, which is the size of a washing machine, and miniaturize that to about the size of a coffee cup, so you can host that on a very small CubeSat. So what you cannot do is miniaturize the antenna, right? So you need the spatial resolution of tens of kilometers. So you're stuck with the lambda over d limit of the antenna. But what you can do is miniaturize all the electronics behind the antenna, and that's really what we've been working on. So folks like the UMass Amherst Radio Astronomy Department have helped us to build. They've actually built a lot of very small, low power, very sensitive receiver systems that make the core of the radiometer sensor. And we've been working with the folks at MIT Air Astronomy Department to figure out, how that could be hosted on a very small but capable CubeSat system. So in the early part and the mid part of the last decade, it involved us trying to figure out how to miniaturize the radiometer, put it on a CubeSat. And the animation in the bottom of the screen, I hope you can see there, shows how this kind of works. So we've got the payload is the first third of the satellite, and it's rotating at 30 RPM. So every 2 seconds, we get a swath across the Earth as the satellite flies. So the Micromass 1 system we launched, and we learned a lot about how to make the spacecraft work and accommodate this. ESTO funded the Murata CubeSat, which was our really first attempt to try to put together multi-band radiometer sounding in a CubeSat. So this had temperature, water vapor, and millimeter wave channels. So I think this spanned 50 to 200 gigahertz. And then it's all culminated with the Micromass 2A mission that we launched in January of 2018, which provided some really great data and showed us that we could, in fact, pull this off. Right? This was a doable do, if you will. So here's a chart that shows the first CubeSat sounding demonstration here. And this channel I'm showing you is a channel near 90 gigahertz on the left, comparing it to the ATMS 90 gigahertz channel. And the data looked very good. We showed that we could calibrate it and geolocate it. And there are a couple of papers and TGARs that came out on how we were able to do this. So this was really the kind of the watershed breakthrough that we pushed off to do TROPICS. Given that we can have this capability, let's scale it up, build a lot of them, and then put them in a constellation to address the revisit rate problem. So there have been some really nice, recent work to push this forward and to take us into the next generation of this. I just wanted to kind of highlight some of the things. So I mentioned Micromass 2A was really the first demonstration of a CubeSat sounder, and this had temperature and water vapor channels. Tempest D came along a half a year after we did with water vapor channels, and they showed that you can get a long life mission out of this. So they lasted, I think, almost 3 years. And I think they only turned off because they deorbited from their ISS orbit, right? So they probably could have gone on a little longer if they were up higher. So they had a relatively long life and a very well calibrated instrument. The orbital microsystems, the GEM system that they were building, they were the first commercial outfit to demonstrate a CubeSat sounder in July of 19. And I'll talk quite a bit about our TROPICS Pathfinder satellite coming up here. This is our qualification unit that we built before we built the 6 Constellation vehicles, just to prove out the design and make sure that all the testing worked. We decided to go ahead and launch that to wring out all the ground elements and the processing and the science and the spacecraft checkout. And that worked very well. And I'll show you some data from Pathfinder. And that was the first CubeSat sounder to give us a global image. The Pathfinder's in a sun-sync polar orbit, so we've got global coverage. And that has worked essentially continuously over almost a year, with some exceptions of when we were doing the bus commissioning and checkout and things like that. And then the final piece of this is it hasn't happened yet, but we hope that it will next month, and that's the Constellation, where we launch 6 more of these TROPICS satellites. And these satellites give us temperature and water vapor sounding, and they also have imaging channels at 90, but also at 205 gigahertz. And this 205 gigahertz channel is very sensitive to ice in the clouds, and it's got very good spatial resolution. So I'll show you some images of tropical cyclones that are very nice from this 205 gigahertz channel. So we've come a long way in the last few years. I think there's a vast potential to use these kinds of systems to further augment and complement the operational network that NOAA has. And I think you'll eventually see that these two kinds of things merge together, that there'll be a hybrid architecture of the big sats and the small sats working together and doing what each of them do well. Okay, so let me move into the TROPICS overview here. So you can see our glorious acronym at the top of the slide there. I'm the PI of the mission, and I've got a fantastic team of folks helping with this. Scott Brown at NASA Goddard is our project scientist. And at the bottom of the screen, you can see all our partners at Wisconsin and NOAA and Goddard, MIT campus, Vanderbilt, great science team. And as you'll see, a really good partnership with some of the new space commercial entities like Blue Canyon and KSAT and Astrospace and others. So the deal here is to measure in 12 channels spanning 90 to 205 gigahertz. And it's all about the high revisit. We want to make these measurements with revisits of about 45 to 50 minutes median over the tropical cyclone belt, and demonstrate that is a really good way to improve our forecasting capabilities and understanding of the storm features and structure and so forth. So I mentioned it's a constellation of 6 CubeSats. So the lower right of the figure shows you a nice photograph of the flight units ready to go. 2/3 of the satellite is the bus from Blue Canyon, and Lincoln Lab built the scanning radiometer there, the top gold cube there with the red cover on it. I mentioned we launched the Pathfinder June of last year, and it's worked fantastically well. I'll show you some data from that. And then we're all, of course, very excited about getting the Constellation launch, we hope, in June or July of this year. I think everything is ready to go. Technically, we're waiting on things like FAA approvals and whatnot before we can launch that, but that we hope will come soon. Okay, so to give you some high-level objectives of the mission here, I just wanted to point out what we're doing with this. So we're trying to take things that a microwave radiometer can measure usefully and relate those to markers that tell us things about intensity of the storm, precipitation structure, anything that we can use to try to understand how the storm might form or intensify, and parlay that into better forecasting. So that's all about the environmental moisture and the precipitation cores, and then finally trying to assimilate the radiances into models to improve the forecast. So I'll give you a couple of examples of OSSEs, OSSEs and OSEs that we've either done or are starting to do to prove that these measurements will be impactful to the forecast. So there are 5 core products that TROPICS will produce, and I wanted to give you a sense of the quality of these. And again, we're talking about passive microwave radiometry, so these are not necessarily state-of-the-art in any given instance, but when you put them all together and have the update rate of 45 minutes, that's really the key achievement of this constellation. So The vertical resolution is not great. It's 3 kilometers or so, but it's good enough to resolve a warm core anomaly in the eye, and it's good enough to move the needle on the forecasting. So for example, we've got a baseline requirement of about 2 Kelvin for the RMS uncertainty on the profile, 25%, and the moisture uncertainty, and the rain rate, and the intensity indicators there, the minimum sea level pressure and maximum sustained wind, are on par with ATMS, or maybe a little worse, but pretty comparable to what we get out of ATMS. And again, the Roll-Wind is having these with a 45-minute update. So our baseline science collection period is 1 year. But we hope that, given the experience of others that have flown before us, that we can do more than that. And Pathfinder, knock on wood, is working great after almost 9 to 10 months. So we're hopeful we can go beyond a year, but that's our requirement. Okay, so here's a pretty busy slide, and I hope the animation in the bottom middle there is working for you. Let me talk about the animation first. And one of the unique features of the constellation is the orbital configuration. So this is not a polar orbit. It's not sun-synchronous. Pathfinder, we launched into a sun-sync orbit because we got a rideshare launch. The constellation is different. They're going to be launched into 30-degree inclined planes with altitudes of 550 kilometers. And we did that to put them over where the tropical cyclones are going to form, right? There are no tropical cyclones near the poles. So we want to get the maximum revisit performance where the tropical cyclones are going to form. So that led to that 30-degree inclined tilt with respect to the equator. So that means we need dedicated launches. Nobody's launching to 30-degree inclination on a rideshare. So we relied on NASA to go out and compete a launch contract, which they did, and they selected Astra Space. I'm actually out here in California today to visit Astra tomorrow to see the rockets that will launch TROPICS. There are 3 rockets that will launch, again, as I said, in June, July, to get us into those specific orbital planes, which will give us coverage up to almost 40-degree latitude, plus minus. With our wide swath, we'll get up to about 40-degree latitude. Let's see. So in the upper left of the slide is some details on the satellite. And again, these are very capable. They're very small. It's the size of a loaf of bread, about 10 pounds. But there is a lot packed into that small volume, right? So just to take you through some of the highlights here. So on the right, you see the solar array, which actually articulates, that moves as the satellite is orbiting to track the sun. And the satellite bus, the silver part there, is rolling as the satellite flies to point the array at the sun and also point the ground, the antennas out to the ground for downlinking. And at the left, that gold box with the circle looking at you is the radiometer. So that's spinning at 30 RPM. So you have all this motion going on. The payload is spinning, the bus is rolling, the array is articulating, and we have to geolocate our data, while all that is going on. So I mentioned the miniaturization of the payload, and the also very low power consumption. So the whole satellite consumes 15 watts average. 3 watts of that is the payload. And just to give you a sense of comparison, so a sensor like ATMS, the payload itself would use almost 100 watts, right? So we've reduced that down to 3 watts through a lot of integration and a new design on the back end of the radiometer to do that. And that's really where the ESTO funding helped us to figure out how to do that. Let's see. So we talked down to the ground over an S-band radio through the KSAT network. The middle upper portion of the slide gives you a sense of our satellite tracks. We have our main ground link in Hartebeesthoek, South Africa through the KSAT-like ground network. So we talk down to South Africa a couple of times a day. So I mentioned this is a NASA research mission, so there are no formal requirements on an operational layover on this, if you will. So we have no latency requirements. I think our latency requirement is about 4 days. But this data, is so useful to the operational analyst and forecast community. They want it much more frequently than every 4 days, right? So we have worked very closely with NOAA to try to overachieve on our data latency. And NOAA's actually funded an exercise with Pathfinder that we just completed that showed that we could achieve 1 hour latency with the data and even 45 minutes for the constellation. So I'll talk at the end about how we might try to provide much improved latency, even though it's not a requirement for our NASA mission. We're not beholden to do that. We're going to try to overachieve on the latency. So I'll have a few words to say at the end of the presentation on how we might do that. The right portion of the slide is all the ground networks. So you see the KSAT light network I mentioned, Blue Canyon doing mission operations for us. and the data comes over to Lincoln Lab where we do science and payload operations processing. Then over to our friends in Wisconsin, the Space Science Engineering Center. They do all the processing to turn the products into level 2 that we've put out to the general public through the JEST disk from NASA Goddard. So that's how the data flows around. Okay, so a few details on what the channels are for TROPICS. I mentioned there are 12 of them spanning about 90 to 205 for those of you who speak this kind of language with the bandwidths and the resolutions and so forth. The resolution is actually quite good for a satellite that is this tiny. For example, the temperature resolution there, the second from the right column, we have 24 kilometer footprint resolution at nadir for our channels. ATMS is about 32, 33 kilometers, so it's better spatial resolution, although it is at 118 gigahertz and not 60 gigahertz. So, I think the ATMS has better vertical resolution, better sensitivity, but we have better spatial resolution, which is useful to try to resolve the hurricane eyes and trying to do the warm core anomaly sensing. And our water vapor resolution is on par with ATMS, 17 kilometers for the water vapor channels and 15 kilometers for the 205 gigahertz imaging channel, which is a little bit better. And the NA delta T's are pretty good. They're on the order of 0.8 to 1 for the 118 temperature sounding bands, and very good for the water vapor bands, near half a degree Kelvin. So overall, a very high performing system, again, even in a very small package. So on the calibration, I wanted to give you a little schematic of how we do that. So again, the animation is showing you the 30 RPM spinning radiometer payload. So we scan across the Earth and take 81 spots across the Earth every scan. Then we look at cold sky. So we have a cold sky calibration, and then we turn on a noise diode. So there's no black body calibration target in the instrument. There's a noise diode that we turn on through the front end to calibrate the system using that. So I'll show you some data here coming up that shows that has worked very well. And you're seeing more sensors use that technique. So GMI has noise diodes. The COVER instrument that JPL has recently launched to ISS uses noise diodes. So you're seeing more and more of this kind of technology. It's really useful for calibration of these kinds of systems. Let's see, I'll point out that our swath is relatively wide. It's a 2,000 kilometer wide swath. And some more details on the resolution down the track and across the track and our beam widths if you're interested in that kind of data. Okay, here are some details on how the payload comes together and how the hardware kind of works. So again, the spatial resolution is dictated by how large the antenna aperture is. So we try to make that antenna aperture as big as we can in that cube for the payload, and then we tuck the electronics around the antenna in the corners and the edges of the cube to the extent that we can. So we have the front end receivers for the GDD is the G-band direct detect system, the WF band RF front end for the 90 to 120 gigahertz system. The WF IFP is a piece of NASA ESTO funded technology to do the back-end processing in a very compact, low-power package. And then on the left side is the scanning assembly with a motor and a slip ring to spin the payload and get the data back to the spacecraft bus for a downlink to the ground. So these pieces kind of snap together and integrate into this cube. Here are some pictures of the flight hardware. The antenna system was very challenging. A piece of engineering because we needed to have two beams. There, if you look carefully, you'll see two feed horns. One of them goes through a dichroic wire grid polarizer, and the other one bounces off. So those align the two bands, the 90 to 120 and the 180 to 205. So we need that with low loss. We need that to work over a broad temperature range, and we need very high beam efficiencies and very narrow beams. Right. So taken all together, that's a challenging set of requirements, but our friends at Thomas Keating made this antenna with electroform horns, and this works fantastic. We're getting beam efficiencies exceeding 97% for the G-band channels and close to that for the temperature sounders. Let's see, the middle top is the receiver that UMass Amherst made for us for the 90 to 120. The scanning assembly in the upper right with the hole for the slip ring to pass the data back to the bus. It's all digital as it goes over to the bus. The back end in the lower left that does the channelization for the 8 channels for the 90 to 120. Control and data handling board, which operates the payload and talks to the bus. And then finally the G-band direct detect, which Virginia Diodes made for us in Charlottesville, Virginia. So very high performance parts, very small, compact, low power electronics that work very well together. And when they're integrated, they look like this. So again, this is the antenna showing all the parts kind of tucked around in, again, in the edges and the sides of the payload to maximize the volume available for the antenna. It's 83 millimeters, about the size of, I told the folks in Hawaii about the size of a slice of pineapple, if you did a cross section of that. So again, it's big enough to get that resolution that I showed you on the previous slide, but small enough to be accommodated on a CubeSat. So it's kind of a very nice fit there. And the scanner is shown on the bottom of the figure. Okay, so we have, again, 7 units. So the 6 Constellation flight units are shown on the right, and the qualification unit, which we repurposed and refurbished for flight for the Pathfinder, is shown on the left. And then you can see the payload spinning and the array moving as it would on flight. And then additionally, the bus would also be rolling. So you get the 3 things going on together. So there are reaction wheels inside of the bus to try to keep everything stable while that's happening. And there are star trackers in the bus that give us our determination of the attitude of where the spacecraft is pointing and how we can determine the bore site of the antenna looking at the Earth. Okay, so as I mentioned, we launched the qualification unit, which we now call the Pathfinder, on June 30th of 2021. We got a good deal on a SpaceX Falcon 9 rideshare launch. They were going to a sun-sync orbit with a 2 a.m. LTAN crossing at a 530 kilometer altitude. So we thought this would be a really good opportunity to check out, essentially do a dry run of the entire Constellation mission. So we did that, and it was very successful. So we were able to check out all the facets of the mission, the ground links and the data processing, science, calibration. All that worked out very well. I'll show you some of the CalVal results that show the data looks very good. We've been able to update and refine some of the processing and get ready for the Constellation. I should say that this qualification unit. So we reserve the best performing radiometric parts for the flight unit. So this qual unit kind of got the dregs of the receiver parts, but it still works very well, and it's been tested extensively. Much higher, testing much higher vibration levels and thermal cycles than you ever would want to do for a flight unit, but we still have gotten good performance out of this. So we expect the flight units to work even better than the Pathfinder has. I mentioned that NOAA has funded a low latency demo. I have some words on that coming up that shows that it's possible to get very low latency out of the Constellation if we're able to get the authorization to transmit and some little extra funding to pay for the contacts. So I'll have more to say about that later. And all the data, of course, will be available to the general public through the Goddard disk system. So let me give you just a few highlights of the Pathfinder mission. So we launched in June with 88 other satellites on this rideshare launch, and it took us almost a month to simply find our spacecraft amidst the cloud of all those CubeSats and small satellites. So we finally did, and we were able to talk to it and very quickly commissioned the bus, and we turned the payload on, and I almost immediately got this picture that I'm showing you right out of the box. So this is, again, the first global image from a CubeSat sounder, and the data looked really good out of the box. You can see the geolocation is working well. You can see some water vapor features in the southern hemisphere. So very quickly, we were quite happy with how good the data looked without too much interaction with it. And then we started making some images of storms, and we're very impressed with what we saw. So this is August 8th. This is Hurricane Ida, which was a big one back in late August. And 3 successive days, so August 28, 29, and 30, as the storm was approaching the Gulf Coast and then making landfall. And this is the 205 gigahertz channel that I talked about earlier. And you can see really nice resolution of the structure, the eye there, and the spiraling rain bands and the structure and around the eye wall. Very nice high resolution data from this 205 gigahertz channel. And then as it makes landfall, that organization kind of dissipates, and you see the rain coming out and the deep blues there. So a lot of really nice imagery from the Pathfinder. And here's an interesting chart. So this is Super Typhoon Mendel in September of 21. So this is our Pathfinder channel. This is the 205 on the right, and this is the NOAA 20 ATMS, their highest frequency channel, which is 183 plus or minus 7 on the left. And it just shows you that this is really good data, right? So the resolution is very good for the Pathfinder, a very well resolved eye, very well resolved structure, in the rain bands near the eye, and high sensitivity to the scattering off the rain band. So this channel is going to be very useful for assessing the structure of the storm and how we might use that structure information to tie back to things like intensification and so forth. So here's a slide that I like that Galina Chirikova and Sierra put together, showing the tropics 91 and 205 on the far left of the slide, and comparing it to some sensors that you're probably familiar with, like ATMS, AMSR, SSMIS, and GPM. So the 90 gigahertz tropics compares very well with the ATMS. Now AMSR, GPM, and SSMI are very large conically scanning systems with antennas that are about a meter across or so. So it's many factors of larger than tropics. So we're not going to compete with that resolution at 90. But the 205 gigahertz channel provides all kinds of great information on the structure of the storm. So we're very excited about the prospects of using the 205 gigahertz channel, and for the analysts and forecasters, I think will find that very useful. And I think the 183 gigahertz might be underutilized today. So the 205 will be even better than the 183 to provide some of the information that we're getting from these big, expensive sensors like AMSR, SSMIS, and GPM that are, by the way, going away, right? So we're not flying very many of these big conically scanning sensors anymore, certainly not as many as we used to. See a couple more examples. So this is Cyclone Baturai over 2 days, again showing the good resolution of the eye and the rain bands. This is our 205 gigahertz channel. And then here is Cyclone Nyan at 90 gigahertz on the left and 205 on the right. And you can see kind of the eye within the eye, the replacement cycle happening there. Very well resolved. Very nice data from Pathfinder on this storm. And we can do more, of course, than tropical cyclone measurement. So here's an example of snowfall, the 205 gigahertz channel on the right, flying over some snowfall in October, compared with the ATMS on the left. And again, you can see that we are more sensitive to the ice and the clouds and the snow with Pathfinder. So I think this is a really nice data set for those of you who are studying snowfall. So this this is not an official product, but I think that there's a lot of nice research that could be done on snowfall using this channel from the Pathfinder and the Constellation when it launches. Here is an image we took of the tornadoes at the end of 2021, resolving, the supercells are moving east. There's quite a bit of a temperature anomaly that we picked up with Pathfinder, again, showing the resolution of the measurements. So I think there are all kinds of interesting things that we can do with the Constellation, with the high revisit, trying to pick up some of these, highly dynamic events that we are missing today with our current polar network. So as I mentioned, we were concerned, at the design of this, that will we be able to geolocate the data with all that motion happening, the payload spinning and the array articulating and the bus moving, and we quickly showed that the geolocation performance was actually very good. We can geolocate the beam to about 1/20th of a footprint diameter. So we're very happy about that, and we've looked at things like coastline crossings to verify that the beams are pointed exactly where we think they are, and getting this really good performance that you've seen here. So that worked very nicely. On the calibration, so as you can probably imagine, we've been comparing Pathfinder data with all kinds of different ground truth. And this example here on this slide is the GEOS5 comparisons. And I'm showing you 3 panels there vertically. The top panel is the 90 gigahertz. The middle panel is the temperature band at 118, and then the lower panel is the G band. And I'm showing you what this is, observations minus the GEOS5 comparisons as a function of the instrument temperature. So as the satellite is going in and out of sunlight, the instrument is heating up and cooling down. So we've got to make sure that our calibration is effective over the entire range of instrument temperatures. And the red vertical lines are the requirements. And for the 90 gigahertz, I should point out that most of the error you see here is not from the calibration, it's due to surface modeling deficiencies. We're very happy with the performance here. For the channels that aren't impacted by the surface, it's down about a half a Kelvin uncertainty, and a scan bias is quite low out to wide scan angles, and it's very flat across instrument temperature, so that's a good indication of robust calibration. So we're meeting all our requirements and getting very good calibration from the Pathfinder. So that's very encouraging, and there's a host of activities going on by our team and others in what we call our early adopter program to look at the calibration of Pathfinder and tease out any interesting features and things that we need to correct and optimize before Constellation launches, which we've been working on. So another interesting aspect is the noise diode, and if you're going to use that for calibration, then how do you know it's not drifting? So we're looking at that very carefully. So the news on that is also very good. So we've looked at this is 6 months of data, and there's almost no discernible drift in our noise diodes for the temperature sounding channels. So that's very good news, and it's in family with what we've seen for GMI, which flies noise diodes at much lower frequencies, by the way, but still they've found that the noise diodes are very stable. So this seems good for calibration for the Constellation. And then finally, a lot of people ask about the NE delta T's, how good is the noise performance? And it's good, it's not great, but it's good enough for us to meet our requirements for the TROPICS mission. The G-band noise is actually very good, and it's very stable. It's down around half a Kelvin or so. And for the most opaque water vapor channel, I believe that's a little better than ATMS. The temperature sounding bands are not as good as ATMS, but again, we have better spatial resolution. So the stability is actually very good over the course of the mission. So that's encouraging. So I mentioned we have 5 core products. So the science team has been working very hard to try to validate the measurements from Pathfinder, get all the algorithms tuned up for the Constellation mission. Here's just some very quick examples. We're using the MIRS system for our profile retrieval for temperature and moisture. So that's looking very good. The Wisconsin group at SIMS, this is Chris Feldman and Derek Herndon, are looking at TCI estimation, as well as Glenn Jericho and Mark DiMaria. They have their own method, so that's looking very good. And then Chris Kidd and his team at NASA Goddard are working on the precipitation retrieval and comparing that to iMerge, and that's meeting requirements. So a lot of very nice work on the product side. We're also doing assimilation experiments, OSSEs, OSSEs, and OSEs. So there's a paper that came out summer of last year. Wade Christopherson published this that shows that the TROPICS data in simulation appear to have a very nice positive impact on forecasting. And then we've started to do OSSEs with actual Pathfinder data. And part of that involves a collaboration with the Cygnus team to try to see if we can synergize the Cygnus measurements with the Pathfinder measurements to see if we can, no kidding, get a forecast impact with actual Pathfinder data. So that work is in the early stages, but I think it's very encouraging. Finally, let me come back to the low latency demo. So the operational community, when I talked to them about TROPICS, is very interested in getting low latency data. So we're trying our best to try to deliver that. So again, NOAA funded an experiment with a Pathfinder to see how good we could do if we pulled out all the stops. How low could we drive the latency? And we could get it down to better than 1 hour with the Pathfinder. And we've shown that using our ground stations at Svalbard and Punta Arenas. So that's great news for the Pathfinder. So that means for the Constellation, if we're able to turn on more ground stations, we can get the latency down to about 45 minutes. And even better, we think, in the Atlantic Basin. So to pull this off, we need 2 things to happen. The first thing is we need frequency authorizations through the NTIA for these additional ground stations. We do not have that yet, but we have requested it. And we're calling in favors to everyone we know to try to get this to happen as soon as we can. So we're hopeful that that will come in at least in time, maybe for peak hurricane season of 2022. The second thing we need is some additional funding for the ground stations to actually collect the data more frequently. So we're working, trying to get a little more funding through some government agencies for that. But we're hopeful that we can turn this on and show a very low latency Constellation product. So stay tuned for more on this. And last, I just wanted to leave you with a little bit of a look ahead to what's next after TROPICS. And I have two things to say about that. Well, here's the first thing to say is that NASA ESTO, as I mentioned earlier, has been very helpful in pushing the constellation, and they've been very helpful recently in funding some new projects for very capable next generation sensors. And I just wanted to point out two of those projects that we're kicking off now. One of them is a system called Cruiser, a configurable reflect array for electronic wideband scanning radiometry. And this is essentially a phased array. Okay, so we can electrically steer a beam from a deployed thin panel aperture deployed from a small satellite. So this does a lot of very nice things for you, right? So you can selectively define where you want to point as the satellite is flying over. So it's got agile beam pointing. It's got very high spatial resolution. If you look at the dimension on this panel, it's almost 2 by 2 meters. So that gives you very fine spatial resolution if you need that. You can point that where you want to, and it all folds up and fits in an ESPA class small satellite. This is all software defined and can be optimized on the fly. So as the satellite is flying and looking at a scene, it can decide where to look and what spatial resolution and what spectral resolution, what channels, all that's all configurable with Cruiser. So ESTO is funding us to build a prototype small scale version of this and test that out. That's through their IAP program and through their AIST, Advanced Information Systems Technology program. We've been selected for funding on a system that's called Video. And what this does is allow us to do a laboratory test bed to test in the lab these configurable sensors. So, and the blue box there in the middle of the chart is a software-defined sensor where, in principle, you can define the spectral resolution, the spatial resolution, where the thing is looking, what the resolution and coverage is, and actually try to feed that back with either a model on the ground or another sensor telling the sensor where to look and how to optimize itself for the best viewing of the scene. And a challenge with this kind of really next generation system is how do you test this on the ground? So we've come up with a system, this is in collaboration with Steve Rising at Colorado State, to use a new radiometric scene generator that is made up of very thin, high emissivity surfaces that we can actually put a high resolution heating element behind and project high resolution spatially resolved scenes into the sensor and have it react. We can test all these software agents that are running on the sensor to do all this. So very hopeful that we'll be able to prove some of these new techniques in the next couple of years for the next frontier of these sensors, which are going to be configurable, very high performance, very high spatial resolution. And finally, I'll just leave you with a kind of a path forward. So again, the big thrust here is on the high revisit measurements that the TROPICS constellation will provide. It's something that we've wanted for many years. We're finally going to get it with the TROPICS constellation with a median revisit of about 50 minutes. I showed you the performance of the CubeSats has been really good, including the on-orbit performance of the Pathfinder. Really good data there, and we're excited to start launching the constellation next month. And then the last bullet there is interesting, is that Tomorrow.io is a company based in Boston. Some of you probably heard of them. They have announced that they're going to fly a radar constellation, and they are going to actually add a microwave sounding component to that constellation and fly the evolved version of our TROPICS payload on that sensor. So you're going to have TROPICS class measurements for many years to come with the TROPICS mission for NASA, and then independently from that, the Tomorrow.io adjunct to their constellation to fly TROPICS radiometers. So with that, I'll stop, and I'm very happy to answer any questions that you might have.
Thanks, Dr. Blackwell. We did have an online text question that was just asked while you were speaking, but everyone else, after this question, feel free to unmute yourself, to raise your hand, to ask a question in the chat, and I will read it out loud. So this question is from Jack Bevan. He asks, will there be imagery of the brightness temperatures so the forecasters can evaluate the TC convection structure?
Yes, absolutely. So Galena, I showed one of her slides. She's working on, I think she's actually done this. All the data will be in Awips too, actually. So it should be very easy for the forecasters to access the brightness temperature imagery in the tools that they're accustomed to using. So we certainly plan on making that available.
Great. Okay, and here is Hu Yang, who has their hand up. Hu, you can go ahead and unmute yourself.
Hi, Bill. First of all, congratulations for the success of Pathfinder.
Thank you.
It's really excited for the whole community, I think. Two questions. One is about the instrument instability and the data continuity, because as you know, the biggest difference, I think, for the miniature, the CubeSat and the normal size instrument like ATMS is how the temperature control. I think for the maybe it is the challenge for the CubeSat to do the good temperature control. So I'm just wondering what the performance of the Pathfinder in terms of the skin stability and also the data continuity. You know, for the, you want to be the operational, you need to be the data very, you know, downlink of the data must be very stable and continuous, and then continuity must be very good. This is the first question. The second question is that I think a lot of people also are concerned about the orbit stability of the small sat, because you have the small size also, and the altitude is 500 kilo, is much lower than the normal polar polar orbit satellite like JPSS, and the atmosphere dragging force should be bigger than the polar orbit satellite. So I'm just wondering what the performance of the Pathfinder, orbit stability and the satellite attitude is stable and something like that. Can you give us some detail about this? Thank you.
Sure. Let me see if I can pick those off quickly. So the first one on the temperature stability. So ATMS has the advantage of a temperature regulated cold plate that it flies on, right? So the temperature that the ATMS sees is very stable over, a few degrees C. So that's great for a radiometer. Yeah. Yes.
Yeah. Still there?
Oh gosh. All right. How about now? Is it better now? Oh no.
Yeah, it's good.
I'm
It's
here.
good. Yes,
I'm
good.
here.
We can hear you. We can hear you. No problem.
Okay. Sorry. Okay, let me get back to it. All right. So yeah, so you're exactly right. So we have no temperature control on. Well, we have minimal temperature control on the tropics. So for that, we need to operate over a very wide range of temperature operating conditions, which we can do, right? So we did all kinds of pre-launch testing and assessments of how the radiometer performs over a relatively wide range of temperatures, and that's why I showed you that figure of the calibration over instrument temperature that shows that we are very stable over instrument temperature. So we do have a much wider temperature swing than a sensor like ATMS, yes, but we've proven that we can calibrate very effectively over that wide temperature swing, so it's not a big deal. Let's see, data continuity. So the availability, there's two issues. The data availability for Pathfinder has been fantastic, exclusive of the original checkout period. So we've been operating near 99% over most of the Pathfinder mission. So that includes the operation of the radiometer and the downlinks. Those are all very stable. And then add to that the low latency we're aspiring to. I think it'll be a very nice, reliable system if all that continues to hold. And then your last question on orbital stability, right? So we are lower than ATMS, NOAA 20. So we're going to deorbit with about 8 years. It'll take us 8 years to deorbit, but still that's a pretty long time. That's much longer than say an ISS orbit. We have maybe 3 years. So we'll be up there 8 years. The orbit will change a little bit, but it won't be a huge deal, I don't think. And the whole idea of these constellations like this is that you systematically replenish them, right? So as one guy ends the end of its useful life after 5 years, say, you've got the next batch going up. So you should continuously have a nice fresh set. And I hope I got all that in those responses.
Yeah, thanks. Great. Thank you. And last, you mentioned about the data sharing, public release of the data. Do you have any schedule for this?
Right. So for Pathfinder, the data is already out for the early adopters. And that will go live to everyone, I guess, as soon as we have the next level of CalVal on the level 2 products, which I think should be pretty soon. And the constellation data will be the same approach, right? So the science team will get the first look, then the early adopters will get the next look, and then the general public will have the look after that.
Great. Thank you. Thank you again.
Sure, thank you.
Okay, sorry about that. Just so you know, I'm having some network issues, so John might take over for me in a second. So here's a text question. What are the 1/F noise statistics? I am specifically curious about the channel error correlations.
Yep. Yeah, that's a good question. So they look pretty good. Let's see. I don't know if I can give you a quantitative answer right now, but I'll say they're kind of on par with ATMS, and the data that I've shown you and the statistics that I quote in those Cal-Val curves. It's all included in there, right? So the NA delta T includes all the 1/F. So it's there. I would say it's on par with what we've seen with current instruments.
Okay, great. This is my last text question, but if anyone else has any questions, oh, I see there's a verbal question waiting, but I'll ask this one first. What are your thoughts / plans for the hyperspectral microwave instruments?
Right. Okay. So I think there are a number of benefits to, essentially the question is, why not go to a digital backend? So if you go to a digital, high sampling bandwidth backend, that gives you the ability to do hyperspectral sampling if you want to. That gives you the ability to mitigate RFI, which I think is going to start to be a problem as 5G, 6G, 7G starts to encroach upon the frequencies we're using for temperature sounding, and it allows you to dynamically configure your spectral passbands. So there's a lot of advantages to moving to digital backends, and hyperspectral operation is one of them. And I think that there are a lot of existence proofs, if you will, for the fact that does offer benefit near the absorption features if you're able to do it. So I think that's certainly going to be the next generation. You'll have digital backends with selective hyperspectral operation, I guess is one way to put it.
Thank you. Our next question, Jack, you can go ahead and unmute yourself and ask it.
Hey, Bill, great talk. I had one question about the slide you showed about the cruiser prototype. Did I see that correctly, that's going to have low frequency channels on it? I thought I saw 24 and 31 gigahertz on it. That would be comparable to the 36 and 19 that we use right now.
Absolutely. Yeah, it would be better resolution than what we get now.
Okay, the one thing that's lacking on Tropics and some of the other similar projects is the low frequency channels, and the high frequency channels are great for mature storms, but the low frequency that are sensitive to the rain are more important for the immature storms, and goodness knows we get enough of that. And
Yep.
Do you have a time you think the first one of those is going to fly?
We hope to have one flying in about 3 to 4 years.
Okay. Sounds very good then. Thank you.
Bet.
We also have another text question. They said, are there any onboard communications between satellites to coordinate with each other?
Yeah, that's a great question. And so for the atmospheric sensing, I guess my answer is not to my knowledge, but boy, I think that is an area of fertile research. Whereas we certainly could, in principle, have these sensors talking to each other, either talking to each other and or talking to the ground. And if you've got a configurable sensor, that makes a lot of sense, right? So you can kind of cue the sensor. Maybe it's the sensor flying behind you in the constellation. Say there's something interesting happening here. Please tune your, point your beam XYZ. So I don't think we're doing that yet, but we surely could do it. And I think there are a lot of plans to try to do that. And I mentioned this NOAA ESTO AIST program. I think one of the things they're looking at is exactly how to enable those kinds of cross links and how to test that. So I think that's coming, but it's not quite here yet.
Thank you. Are there any other questions? That's it for my queue. But if you have a question, a last minute question, you can just unmute yourself and ask it, or just ask me to do that in the chat. Oh, here's from Juan Meng. Could you please comment on synthetic aperture microwave sounder for GEO satellites?
Wow. Okay. So synthetic aperture for GEO. All right, so putting a radar on geo is a very tall order because you're so far away from the Earth. So that I think that's maybe your first challenge is that's the R to the fourth power is hurting you for the geo. So, but there are SAR systems coming online and in LEO, and there's some interesting commercial SAR systems in LEO that are coming online. But those typically aren't used for atmospheric things, although I suppose that you could do some interesting things there. But that's certainly a burgeoning area, the SAR. And the SAR geo, I'm not familiar with at all.
Oh, here's another question, text question from Young Kun Lee. They said, you showed the mirrors retriever results. How many profiles were included in the results? The reference is ECMWF or GDAS.
Okay, so let's see. So I believe the slide that I showed that had the 5 products on the CalVal, that was only a handful of profiles that were run through mirrors. So I think that we've run through, let's see, so we've compared with ERA5, we're compared with radiosondes. So, I think we're at the level of, hundreds and thousands of profiles now, maybe not, millions, but thousands. And I think the question was about what are we using for backgrounds or references, first guesses, maybe. And I think the first guess for the mirrors is derived from GEOS5. There's a couple of things that we're looking at there, alternatives to that, climatologies or other options.
Okay, and if either of the last 2 question askers want to unmute themselves to elaborate or discuss, now's the time. Or if not, new questions are also welcome, but we're also approaching the end, so. Okay, well, unless someone interrupts me, I'm going to close out today's seminar. Thank you, Dr. Blackwell, for giving us this talk. This is actually the second time Dr. Blackwell has spoken in an Essex seminar. Both times have been awesome. I think the first time is also on YouTube. I should have said that in the beginning. So now there's a double feature. And thank you everyone else for showing up and listening and attending our seminars this semester. We do have one more remote seminar that is next week. Yes, that's next week. So please show up next week and have a great week otherwise. Thanks, everybody.
Thank you.
Thanks, Bill.
Thank you.
You bet, John. Thanks, everybody.